Good morning, everybody. Well, a few bodies who are here. Let me go ahead and share my screen. I apologize. Starting a little bit behind. Hold up. Okay. We're gonna start chapter 5 today, which is thermochemistry, and I'm gonna give you. But today is just a bunch of definitions, things like that. But I'm gonna give you the high points out of the chapter because we're up against it, but we're still gonna get everything covered that we need to cover. Um, but yeah, so let me give you today is again a bunch of terms and definitions. So um, yeah, probably the most boring class that we've had all semester. Some of y'all might beg to differ, but for me, definitions and terms, I hate it, but we need the foundation. So there are some things that we're going to be talking about in this chapter. Um, which is dealing with thermochemistry. All right, so we're going to a lot of terms you've heard before: heat, temperature, thermal energy, specific heat. Um, all of those terms are going to be defined and distinguished because there's a difference between heat and temperature. There's a difference between thermal energy and temperature and things like that. So we're going to make those distinctions between um, those different topics and then do calculations based on specific heat and temperature change and things like that. So if you think about a chemical reaction, A going to B, just any given reaction, it's going to have an associated change in energy, right? So all chemical reactions have a change in energy. Uh, right? We think about energy being converted from one type to another, matters being converted from one type to another. And so in any reaction that you do is going to have some energy change. Sometimes it may absorb energy. Right? If it absorbs energy, then we call the reaction endothermic. Right? If it uh, releases energy, then we call it exothermic. Right? But at any rate, if there's always going to be some difference in energy if you when you do a chemical reaction. So what thermochemistry studies is this phenomenon, like how much heat is released or absorbed during either chemical or physical changes. It's the study of amount of heat either lost or absorbed during a chemical or physical change. Right? Because there are some physical changes that also happen with changes in energy. Now you think about uh, taking even if you're cooking, right? The pot, if you're heating that pot up, but it's not changing, it's not being converted into another form of matter. It's just increasing the temperature. Uh, and then if it cools off, that's also a physical change because you're not changing the state or the type of matter. You're only changing the temperature, right? So physical changes also are included. Um, and what energy, we're going to define that energy, and we're also going to define work. You've heard all these terms before. Somebody tell me what your definition of energy is. We hear that word thrown around a lot too. Bad energy, negative energy, draining my energy, sapping my energy. But the scientific definition is the capacity to supply heat or do work. Right? That's the scientific definition for energy. Energy is the capacity or the ability to supply heat, which is a type of energy, thermal energy, or do work. Right? And work also has a definition. Right? It is the process of making matter move against an opposing force. Right? So energy is the capacity to supply heat or the capacity to do work, and work is the process of causing matter to move against an opposing force. And you know that there are two types of energy, right? There's potential energy and there's kinetic energy. Uh, I'm sure you learned that in high school physics as well as high school chemistry, right? So potential energy, kinetic energy. Kinetic energy is derived from motion. Potential energy is derived from position. Right? We're not going to go into all the different aspects of these. It's just laying some groundwork. And anytime we think about energy, there are different types, right? So energy can be converted from one form of energy to another, right? So kinetic can be converted into potential, potential can be converted into kinetic, so on and so forth. So with that being said, we have to think about energy now in terms in terms of what we're discussing with thermochemistry. We have to think about energy in terms of thermal energy, temperature, and heat. Right? Because they're not the same. Thermal energy produces heat, and heat is measured by temperature. All right. So thermal energy is how do I put this? It's a result of atoms or molecules moving, right? So thermal energy is derived from the kinetic energy of the motion of atoms or molecules. and this is important. I have to make this point. Nothing is static. Everything is moving, even on the molecular level, on the atomic level, on the subatomic level. Nothing sits still, right? I know when we write down, uh, let's say we write down a reaction like this, where we have sodium chloride plus, let's say, calcium carbonate. And that gives me sodium carbonate plus calcium chloride, right? So I'm gonna put a 2 here to balance it. And that'll balance the sodium and the chlorine. We think about this like, oh, we just wrote this reaction down. But in reality, the atoms are literally, if we write this in ionic form, right? These atoms are literally colliding with one another on a atomic level, colliding with one another, and then that's how the double displacement actually happens. So nothing is static. Anytime you see a molecule written out or a compound drawn out, that thing is not just sitting there, right? Even materials that you think are static, like you have your desk, maybe your screen for your laptop, whatever. Even those, the molecules are moving, but sometimes they're moving so slow that you can't tell, right? Everything is moving. So the thermal energy is given off by the kinetic energy of uh, atoms or molecules that are moving. And as you can imagine, if the atoms or molecules are moving very slowly, they're not going to give off much energy, right? And so when we think about the temperature is basically a measure of how fast or how slow that kinetic well, let me not say that. It's a measure of how fast or slow those atoms or molecules are moving. Because if they're moving really fast, they're going to have high thermal energy, which is going to also result in a high temperature. So what is, let's define temperature. Because temperature is quantitative. You can actually put a number on it. So it's a quantitative measure of what we call hot or cold, right? But hot and cold have their own definitions. Something that's hot means that it has a high thermal energy, and the atoms or molecules are moving at high velocity or high speed, right? So that's we can say that when those atoms move around a lot, that means that the thermal energy is going to be increased. It means that the temperature is going to be what we consider hot, right? Think about hot water versus cold water. When you think about hot water, those water molecules are all over the place because they're moving so fast, and that's what causes the temperature of the water to go up, right? Versus cold water, where the molecules slow down and the temperature of the water is not as high, it's not as elevated. So something that's hot, atoms or molecules are moving rapidly, and then something that's cold, this is going to have low thermal energy, just the opposite of what's hot, right? And it's also going to have low velocity movement, right? So hot stuff has a lot of thermal energy. Cold stuff does not. And it's that simple. The other part that we think about when we think about hot and cold is when something heats up, it expands. When something cools off, it contracts. A good illustration of that is water again. Hot water, when you heat it up to a certain point, what happens to it? Does it just get hotter and just stay liquid? What happens to it? If you turn the eye of the stove up past 100, like where the temperature of the water can get past 100 or 100 or higher, what's going to happen to that water? Is it going to boil? Is it going to be converted into a vapor? Or is it just going to sit there? All right. So if you heat it up, it's going to expand. If you're cooking, and anytime you cook, maybe if you cook greens or you boiling something on the stove and you put a top on that pot, when that water starts boiling, that top is going to start vibrating. And that's because the vapors are going to be trying to escape because of expansion. It's trying to expand, right? Same token with ice. You cool it down enough, the molecules start to contract, get closer together, and you go from a liquid to a solid, right? So at low temperature, things contract, higher temperature, things expand. So we know what temperature is. It's a measure of hot or cold. We know what thermal energy is. And then the other part of this is heat. So if I have two bodies close to one another, and this one is hot and this one is cold, heat is going to move from the hot body to the cold body. That's how that works. So this is, if it's hot with high thermal energy, right? And this is low thermal energy, right? The hot body is going to give off heat and the low body is going to absorb heat, right? So this gives heat and this absorbs heat. And because of that, they eventually equilibrate. Right? They eventually will equilibrate where they're both at the same temperature. But initially, it's going to be what the hot body giving off heat to the cold body. So heat is basically the transfer of thermal energy. Right? Transfer of thermal energy between two bodies at different temperatures. I'm abbreviating between. So two bodies at different temperatures, the heat or thermal energy is transferred between them, and that's how we define heat. Right. So again, if you think about this in a practical sense, I don't know like how many of you have ever been to Mardi Gras, but I'm from Mobile, and when we go to Mardi Gras, normally in February it's really cold. So what you do is you get you a crew of people and y'all stand together, and that's because you can transfer heat from one body to the next. So one person who might have had a little extra hen that night, they may be giving off a little more heat than the person next to her, And so that's, I mean, that's literally what heat is. It's the transfer of thermal energy between, when I say bodies here, I'm not talking about human beings. We're talking about just two entities, right? Maybe two substances or two things, but it's literally the transfer of thermal energy between two bodies at different temperatures. And it always equilibrates. The thing that's hot is going to give it's only going to be able to give off so much thermal energy before both bodies reach the same temperature, right? So that's why I say that it will eventually equilibrate. Let me just expand this definition. So both will eventually have the same temperature. All right, so once you get to that point, then there's no more heat transfer. All right. So when we think about all of this stuff in totality, heat, temperature, thermal energy, we have to have a way of measuring it. So the way we measure it is with different units, and this is really, really important. Normally, heat and energy are measured in either calories or joules. Heading up here. Right? Calories are used often to measure energy and heat, and normally when we think about calories, we think about like the food that we consume, how many calories are in a Snickers bar or whatever. But calories, that's a measure of energy, all right? And a calorie is the energy necessary to take 1 gram of water and raise it by 1 degree. So that's how we define calories. Right? So 1 degree Celsius or 1 Kelvin. And if you remember, Kelvin is 273 plus degrees Celsius. That's how we convert Celsius into Kelvin. Right? So again, the calories are dependent on certain external factors like pressure and like atmospheric pressure, things like that. So joules is another way to measure energy without the effect of external factors, right? So when you think about the term joule, it's the energy used when a force of 1 Newton moves an object 1 meter, right? That's the basic um, units for joules. So it's the energy required. So 1 Newton moves an object 1 meter. All right. And the units for joules, right? We say joules, but joules is actually this is one of our SI units for heat and for work. And so 1 joule is 1 kilogram meter per second squared, right? And if you had physics already, or you're taking physics, this is a mass, this is acceleration, right? Which when you take the two together, gives you force, mass times acceleration, right? So 1 joule that's the units for joules. And the reason I say that is because when we're thinking about applying or using these units in calculations, we have to remember what terms make up the unit, so that when we're doing calculations, we'll know how to cancel things out, right? So that's basically why I'm giving you the units. The units are very important, because without the units, you can't cancel out certain terms. And if you can't cancel out certain terms, then you got a problem. All right. So let's look at another extension of this, of all of this information. So temperature, heat, energy, all of this is leading us up to this point where we can actually start talking about heat capacity, right? So there are two terms here that we're going to talk about for heat capacity, and that is heat capacity and then specific heat capacity. All right. So now let's think about this. So heat capacity itself is capital C, and it's Q over delta T. And I'll explain all of the terms. So Q is the quantity of heat. Delta T is the change in temperature. Right, and C is the heat capacity. All right, and this is what we call, if you remember from early on in the semester, this is an extensive property. In other words, it's dependent on the amount or the type of matter. So it's dependent on the type of matter and the amount of matter. So it's what we call an extensive property. All right, and so the specific heat capacity, or the heat capacity, is the quantity of heat that a body of matter absorbs or releases when it undergoes a temperature change. All right, so let's write that over here. So the quantity of matter that's either absorbed or released when it undergoes a temperature change of at least 1 degree Celsius or 1K. Right? So when we think about specific heat being extensive, it changes based on how much of a material is present. Right? And then we think about, I keep saying specific heat capacity. It changes based on the amount of material that's present. Specific heat is different because it's intensive. It's independent of the amount, right? Plus, it's the ratio of two extensive properties, right? So mass and heat are extensive. So you take the ratio, they become intensive. So specific heat, which is lowercase c, includes the mass. Right. So this is it's my heat. This is mass, and then this is temperature change. All right, and the temperature change is always measured in the final temperature minus the initial temperature. Right, so when you see that delta T, it's just a change in temperature, and it's always final minus initial. All right, so the specific heat capacity is different because this is now intensive. It is irrespective of the amount. Right, it only depends on the type, not the amount. So this is going to be specific to certain types of matter, like iron, like aluminum, like carbon, like water. Everything has its own specific heat capacity. Right. So specific heat capacity is similar to heat capacity, but it includes the mass now. So it's the quantity of heat, that's Q, that's required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Or 1K. Right. And so with the specific heat, when you look at these equations, you can think about how to manipulate them. Right. So let's, because we always want to think about the relationships between the terms in an equation, so we can solve for what we need in the case of having to figure out one or the other term. So for heat capacity, big C, that's Q over delta T. What that means is that we can solve for Q, which is big C times delta T, right? So we can solve for that if we, as long as we know the units and what we can cancel, we can solve for it. All right, and even we can also solve for delta T, right? That's the relationship. That's how we manipulate that for heat capacity. And we think about specific heat capacity. This is C, lowercase c is Q over M times delta T. So we want to solve for Q. We can just say Q equals C times M times delta T. If we want to solve for M, that'll be Q over C times delta T. Right? If we want to solve for delta T, it'll be the same thing. Q over C times M. So it's really important to understand how the terms relate to each other so that I see that your answer to that question about the boiling water, Maya. I didn't see it when it popped up though, but thank you. All right, but understanding the terms and how they relate to each other and what their algebraic relationship is to each other is important, because sometimes you might be given one thing, but you got to solve for something else. So you need to know how to, we've been talking about this for the whole semester, how to manipulate equations to get what you want. All right, so let's look at a couple of examples here. right? So let's say we have a flask with 800 grams of water, right? And the temperature changes from 21 degrees Celsius, let me put the unit, to 85 degrees Celsius, all right? 85 degrees Celsius. So that's my temperature change. I have my mass. And what I need to know is um, I want to find out what Q is. Because C is a known value. The specific heat capacity for water is 4.184 joules per grams degrees Celsius. Right, notice the units. We have a heat term, a mass term, and a temperature term. Same thing up here, right? That's what we would solve for: heat, mass, temperature. Right, so the specific heat is a function of all three of those. That's why the unit looks like it looks. It's joules, which is the heat per gram degrees Celsius. And so we want to solve for Q. We know the equation. So we want to solve for Q. We just need to do what? Rearrange this. Which is C times M times delta T. So we plug those numbers in. Q should be in joules. So let's put the numbers in, and we're gonna leave the mass in grams. We don't have to do any conversions there. The C is a given term, so let's plug those numbers in. So this is gonna be 4.184 joules per gram degrees Celsius. Very important. And the mass here is going to be 800 grams. And then the change in temperature, it went from 21 degrees to, the 8 got cut off, 85 degrees. All right, so that's going to be, let me put it up here, T final minus T initial, which is delta T, right? So it's 85 minus 21, so it's going to be 64 degrees Celsius. Right, and that's going to give us Q. Notice what's going to cancel. Grams are going to cancel. Degrees Celsius are going to cancel, and I'm going to be left with joules. Because Q, the unit for Q is joules. Right, because that's the heat. So heat is going to be measured in joules. Notice heat is a type of energy. We're not measuring temperature. So Q is not temperature, it's heat, which is thermal energy. So you measure it with a term or measure it with a unit for energy, which is joules. All right. All right. So what do we get from that? Calculator out. We got 4.184 times 800 times 64. So Q in this case is like 214,221 joules. Normally, a number that size, we write it in scientific notation, right? So we'll say 2.14 times 10 to the fifth joules. 10 to the fourth, my bad. Yeah, 10 to the fourth. 2.14 times 10 to the fourth joules. Did anybody else get that? And this is important to understand how these units get derived, because grams will cancel with grams, Celsius cancel with Celsius, and then joules are my unit that I'm left with. All right. Any questions about that? Let's do one more before we stop. Let me see. I saw something going in the chat. Okay. Thank you, Maya. I see it. I see it. All right. Let's do one more. But this time we're going to have to solve for a different quantity. So we have a unknown metal. And if we find we're going to be solving for C this time, and that'll help us to find what metal it is. So we got an unknown metal. And it absorbs, it has a mass of 348 grams. And it absorbs 6.64 kilojoules. This is a remember that prefix kilo means 1,000. So 6.64 kilojoules of heat. And the temperature change is T final is 43.6. T initial is 22.4. And we're going to solve for C, right? So remember, C is Q times the mass times delta T, right? Now, what we're going to have to do here, though, because this has to be joules per gram degree Celsius. So we need to convert kilojoules into joules. And all we do for that is we can divide it by 1,000, right? So 6.64 kilojoules well, actually, we're going to multiply by 1,000 times 1,000 joules over 1 kilojoule. That's going to cancel. So when you see kilojoules, you can actually, and since it's already that the number is written 6.64, we could actually just write it like this, 6.64, and turn that prefix into what it stands for, times 10 to the third joule. We can do that, right? So if we put that number in for Q, and divide that by the mass of the metal, which was 348. And the change in temperature, which is 21.2. We can solve for C, right? So let's do that. All right, so that's that. 6640 is the top number divided by 348 times 21.2. Make sure I got that part right. 340. Hold up 1 second. So we got 6. Parentheses in times. Anybody got it yet? So C is 0.900. We'll leave it at that. And it's joules per grams degrees Celsius. Can somebody Google that number real quick before we stop and tell me what metal has a specific heat of 0.9? Because you can determine the identity of the metal if you know the specific heat. Anybody found it yet? Let's see. Well, there's a list in the book. Let me see what that. It says aluminum based on the chart in the book, but it's not. It's right at 0.9. It's actually 0.897, so it's rounded up. But it's saying it's giving us the aluminum as the metal. Let me put that in, because that's the closest one to it. All right, so we got to stop here. We're gonna pick this up on Monday, and we're gonna keep pushing with this chapter. So on Monday we're gonna talk about calorimetry, and then we're gonna talk about enthalpy and entropy and free energy. We're going to get all that covered, and that's really that's the extent of what we're going to cover in this chapter: enthalpy, entropy, and free energy. We got to hit all three of those, and then a little bit of calorimetry. All right. Any questions? Okay, which number, Maya? The 0.897 or the 0.9? The 0.897. Okay. All right, cool. Yeah, the 0.897 I took from the chart in the book, which is for aluminum. So it's the 0.9 is actually it's closest to aluminum. So that's what we'll say, that the unknown metal is aluminum. All right. So we'll stop here. We'll pick up on Monday, God willing, and y'all have a good weekend.
You too. Thank you so much.
All right.